Hi all, I welcome you all to the next lecture today. Today we are going to see in detail Otto cycle, diesel cycle, dual cycle, then we'll go for Brayton cycle. In previous lecture I given you some idea about the Otto cycle, right, and also different terminologies used in piston cylinder devices got discussed with you, and also we have seen the classification of power cycle. Let's start our discussion for today. So let's go for Otto cycle. As I mentioned, on Otto cycle there are four processes: two reversible adiabatic processes and two reversible constant volume process. Heat addition and heat rejection usually take place at constant volume, and work compression, work expansion will take place at reversible adiabatic process. So look at PV diagram. This is pressure versus specific volume diagram. These are the constant volume lines, right? And these are the isentropic processes. So process starts from 1. So 1 to 2 is compression process, right? Compression process. So unit mass of air comes in and it undergoes the compression at reversible constant, reversible adiabatic process from 1 to 2, and heat addition takes place at constant volume, right, between process 2 to 3, followed by the reversible adiabatic expansion where we get the mechanical work out of it, right, process 3 to 4, followed by the heat rejection in an heat exchanger in the process 4 to 1 at constant volume. So process 1 to 2 is isentropic compression, and process 2 to 3 is reversible constant volume heat addition, followed by the isentropic expansion process 3 to 4, followed by the constant volume heat rejection process 4 to 1. This is the process. So this is the bottom dead center initial point, this is the final point top dead center. So over temperature versus entropy, if you draw it, isentropic lines will be vertical lines, right? So process 1 to 2 is isentropic compression, followed by the heat addition. When you are adding the heat, temperature will rise, so you reach around 3. Then expansion, 3 to 4 is isentropic expansion, followed by the heat rejection to the initial point. So these are the constant volume process. This is specific volume constant, specific volume constant, right? Heat addition, heat rejection. Look at these. This line length is bigger because work of expansion will be more. You will get more mechanical work compared to the compression. Compression will require less work. That's why length of process 1 to 2 is lesser than the length of process 3 to 4. Similarly, here you can see 3 to 4 is slightly bigger compared to the process 1 to 2. So efficiency can be given by W net divided by Qn, or you can say Q net divided by Qn. So Qn minus Q out divided by Qn, or you can say bar minus Q out divided by Qn. So Q out is process 4 to 1 and Qn process 3 to 2 to 3. You can find out the heat input and heat output. You divide it, you will get the efficiency. So if we do so, we get the efficiency of Otto cycle is equal to 1 minus 1 divided by R to the power k minus 1, where R is known as compression ratio. Compression ratio, as I said, that is the ratio of volume at top dead center divided by volume at bottom dead center. Sorry, volume at bottom dead center divided by the volume at top dead center, right? So or you can say R is equal to volume at 2 divided by volume at 1. So compression process 1 to 2, right? So compression ratio will be volume at 2 divided by volume at 1. This ratio is known as compression ratio. So from this we can say the efficiency of Otto cycle is a function of compression ratio. Higher the compression ratio, higher will be the efficiency of Otto cycle. But there is a limitation on compression ratio. We cannot go beyond certain compression ratio because of the pre-ignition detonation problem of the fuel. So this is the range basically of the compression ratio used for the Otto cycle. So this is the efficiency of Otto cycle, this is the compression ratio. So this is the ideal range, right, where you will get the better performance. So hardly you can go up to 10 compression ratio. If you are going beyond 10, then chances of pre-ignition of fuel will take place, and the operation will not be smooth, and that may cause damage to the engine. So this curves, this is for the gas which is having gamma value of 1.3, This is for air, right? Air will give the intermediate performance, gamma is equal to 1.4. If you are going for helium, right, a monatomic gas, right, for that it is 1.667. In that case, performance will be slightly higher. What is the reason for not using high compressor ratio? Already I given you. There are a lot of problems, right? Pre-ignition is the one biggest problem. Pre-ignition is nothing but you are desiring the ignition to happen at somewhere temperature 400 degrees Celsius. But as we are using high compressor ratio, ignition will start much earlier than that. It may start at 300, but you are ready for initiating the spark at 400 degrees Celsius. That means before the initiation of spark itself, your combustion will start. That problem is called pre-ignition. Pre-ignition occurs in a cylinder that will cause a noisy operation because it will be called as a this explosion into the cold compressed air, right? And because of that, lot of vibration issues will come into the piston cylinder device, right? And because of that, engine may fail. So there are these four causes: premature ignition. Because of premature ignition, as I said, it will create a lot of noise. So that is called knock, right? And reduces the efficiency and mechanically need a better design. So in order to avoid these kind of thing, you have to use heavy panels, right, for combustion chamber design. In that case, weight penalty will be there. When weight of vehicle is more, then specific fuel consumption will also deteriorate. Means it will be very high. But as if you want to improve the thermal efficiency of the engine, then with a high performance, means high compression ratio, you can go up to compression ratio 12 if you are using the gasoline blends, right, with good anti-knock characteristics. But gasoline is slightly, costlier compared to the petrol. That's why, in ordinary, vehicles, we do not go for very high compression ratio. The range is basically typically between 8 to 10. Most cars made since 1975 have been designed to use unleaded gasoline, right? And the compression ratio has to be lower to avoid engine rock. So we are not using the leaded, right? If you are using tetraethyl lead, then you can go up to the compression ratio of 12, right? But this can be used only with gasoline. Gasoline is slightly costlier, right? But as the competitive market requirement, we usually using the petrol, and petrol pre-ignition problem is there. To avoid that, we can go to the compression ratio up to 8, right? In worst case scenario, it can be up to 10. All right. So then after that, the next engine, if we focus on next engine is diesel cycle. So in auto cycle, what was the drawback? As I said, that there is a drawback that we cannot go for very high compression ratio. So hardly you can go to the compression ratio up to 8, and you can go more, in worst case scenario you can go up to 10. And a reason for not using high compression ratio is that pre-ignition detonation issues are there. To avoid that, what do we need to do? Earlier we were compressing the air and fuel mixture. So instead of compressing air and fuel mixture, we can compress air alone. Then once we have reached at certain temperature, right, we can use high compression ratio so that the temperature of the air becomes greater than the self ignition temperature of the fuel. The moment you send the fuel inside, combustion will occur, right? Combustion will start, and your process follows. Mechanical work you can get. That means diesel engines do not require the spark plug. That's one advantage. And process will be slightly smooth because you are compressing only air here, so there is no problem of pre-ignition or detonation in the engine, right? But in the case of petrol engine, that is a big drawback. So it was basically invented by the Rudolf Diesel, right? He was born in Paris in 1858. After graduation, he was employed as a refrigerator engineer. However, his true love was about the engine design. So in 1893, he published a paper describing an engine with combustion within a cylinder, the internal combustion engine. So in 1894, he filed a patent for this new invention. So basically, in 1892 itself, he has proposed a new type of engine that is called diesel engine. So he did a lot of experiment. In one of the experiment, he was almost killed, right, by his own engine because it was exploded when he was testing it. He operated his first successful engine in 1897. So as I said that in diesel, what advancement he has made, he actually what he instead of compressing air fuel mixture, if we compress just air alone, right, at very high compression ratio, then we inject the fuel. In that case, what will happen? First of all, you don't need any kind of fuel, it means spark plug, right? That is one advantage. Another p ignition problem will not be there, right? And if we are using high compression ratio, efficiency will be high. So diesel engine avoids pre-ignition problem by compressing only air and then spraying the fuel into the cylinder after the air is hot enough to ignite the fuel. The spraying ignition is done as the piston begins to move outward at the rate adjusted to maintain approximately constant pressure. So diesels typically have compression ratio of about 20, so you can go up to 20. So engine operating in this way is called as compression ignition engine, or you can say CI engine. So this is the pressure versus volume diagram, right? So what basically has been done? The heat addition that you are carrying out, that means you compress the air alone at a very high compression ratio, then you are adding the fuel, the process is approximately at constant pressure. So process 1 to 2, similar like Otto cycle, reversible adiabatic compression followed by the reversible constant pressure heat addition. Then followed by the expansion, reversible adiabatic expansion, then heat rejection is taking place at constant volume. Look at only heat addition process being replaced by the constant pressure process. So 1 to 2, then 2 to 3 the constant pressure heat addition, followed by the 3 to 4 basically expansion, alright, then heat rejection. So this is the PV and TS diagram of the diesel cycle. So if we derive the expression for efficiency, right, efficiency can be given as 1 minus 1 divided by gamma into 1 divided by RK, this is known as compression ratio, into RC to power gamma minus 1 divided by RC minus 1, this is known as the cutoff ratio. Cutoff ratio means the point you are starting the fuel, the point where you are cutting off the supply of fuel. So fuel basically getting added between the process 2 to 3. So cutoff ratio is the ratio of volume at 3 divided by volume at 2, and compression ratio is the ratio of volume at 2 divided by volume at 1, because process 1 to 2 is compression, process 2 to 3 is called heat addition. So look at this term. So as per this, RC value will always be greater than 1, right? Cutoff ratio will be greater than 1. So, but this is having one extra term here. So, efficiency of diesel cycle will be slightly lesser than the Otto cycle for the same compression ratio. So, diesel cycle is less than the Otto cycle for the same compression ratio. But if we are operating at maximum pressure condition, in that case, efficiency of diesel cycle will be greater than the Otto cycle. So, this is the range of compression ratio in which your diesel cycle can operate. So this is the diesel cycle efficiency, and this is the compression ratio. You look at the range, optimum range. Optimum range means where you can get the maximum efficiency, lies between 12 and 22. So you can go up to 22 compression ratio in the case of diesel engine to get the better efficiency. So cutoff ratio will have some value, right? 2, 3, 4 in the case of diesel engine, but cutoff ratio will be exactly equal to 1 in the case of Otto cycle. So Otto cycle is having range between 8 to 10 only, but in this case compression ratio range has increased. But for the same compression ratio, if you compare, then efficiency of diesel engine will be lesser than the Otto cycle, right? That's the main drawback. Now come to the thermodynamics of dual cycle. If you look at the dual cycle, that means it will have advantage of both Otto and diesel cycle. So that is compression process here, then heat addition takes place at constant volume, right? Part of the heat addition takes place at constant volume, then part of the heat addition takes place at constant pressure. That's why we are adding the advantage of both, right? In Otto cycle, heat addition at constant volume, diesel at constant pressure. So we are adding heat addition into separate form, right? Two parts, part part of heat will be supplied at constant volume, part of heat will be supplied at constant pressure, followed by the expansion and heat rejection process is similar like at constant volume. So if we draw this, right, you can draw this process 1 to 2 is reversible adiabatic compression, followed by reversible constant volume heat addition, then 3 to 4 reversible constant pressure heat addition, then expansion, then rejection at constant volume. So if we draw this over temperature versus entropy, process 1 to 2 is isentropic process, compression, followed by constant volume line, right? This is a constant volume process, and keep in mind the slope of constant volume line will be higher than the slope of constant pressure line. This is a constant volume line, process 2 to 3. This is heat addition at constant volume, then constant pressure heat addition, followed by the expansion in 4 to 5, then finally heat rejection at constant volume. So it is having total these 5 processes, process 1 to 2, 2 to 3, 3 to 4 and 4 to 5. Next one is gas turbine cycle. Alright, these are rotary cycle, right? Those were reciprocating cycle till now. What we have discussed, auto, diesel, and dual. These are reciprocating types of engine. Now we are talking about gas turbine cycle. These are the rotary types, right? So it is similar like this. It will have a compressor coupled with a turbine. In between, there will be combustion chamber, right? So air enters into the compressor, getting compressed, and then compressed air enters into the combustion chamber where heat is getting added, right, from some external source. If you are talking about ideal cycle, if you are talking about actual condition, then burning will take place, fuel will add into the compressed air and burning takes place in the combustion chamber, and hot temperature gases strikes over the turbine blades and turbine rotates and it produces the sufficient work, right, which is required to run the compressor. The compressor is a work consuming device, and also excess work, right, excess rotational work will be utilized to produce the mechanical work or electrical work, whatever you want to get out of it. Shaft is rotating, shaft can be coupled with the generator to generate the electricity, then hot gases, right, the combustible product exhaust to the atmosphere. This is called open cycle gas turbine. There is another brand, right, called closed cycle. So open cycle, as per the power requirement, you can go for single spool configuration. Single spool means one compressor, one turbine configuration. Some cases there will be two turbines, right, coupled with the compressor. This is called basically twin spool, right. One will be high pressure turbine followed by the low pressure turbine. So high pressure turbine will be coupled with the high pressure compressor, right, and then low pressure turbine. So if we are using two turbine, means work output will be enhanced, right? We can enhance the mechanical work output from the cycle. If we are going for more number of stages or more number of cycle, more number of turbines if you are using, or spools if you are increasing, right, two spool or three spool, power output will be more, right. Process same, it takes the air inside, right, and compression takes place, then combustion followed by the expansion, partial expansion in high pressure turbine, then remaining expansion in the low pressure turbine. Low pressure turbine is coupled with the generator where you are getting the mechanical work output. So this is basically open cycle gas turbine. So this is one of the pictorial presentation of industrial gas turbine. So it is similar like this. This is a load, right, where you are getting the mechanical work. So this is the compressor, right. From this side you will compress, take the air inside. Compression takes place. Combustion chamber, here combustor will be there. Where combustion will take place. This can kind of things you are seeing here. Here combustion will take both side. These cans will be there where combustion takes place. And finally, these are the turbines, right? And the turbine is connected with the load where you are getting the mechanical work output. This is the example of aircraft gas turbine, right? When you return back to the Shastra in our aerodynamics lab, you will see one of the prototype of this gas turbine engine. So look at the gas turbine engine. This is the compressor, right? Through it air enters, right? And this compressed air, and finally here combustion takes place. These are here engine, these cans will be arranged where combustion takes place. Finally, this is the turbine stage, and finally it getting exhausted through the nozzle. So in this case, nozzle will be attached at the end, and nozzle will expel the air at very high velocity, and you will get the thrust. You will get the thrust. This is the open gas turbine cycle, right? You look at the fresh air enters, right, in the compressor, and compression takes place within in the process 1 to 2, right, at a reversible adiabatic process. Then process 2 to 3 combustion takes place where heat is getting added reversibly at constant pressure, followed by the expansion 3 to 4 in turbine at reversible adiabatic process, and finally combustible product expelled to the atmosphere, right, exhaust to the atmosphere. Then fresh air again comes in and process repeats. So this is an open cycle gas turbine. So if we draw this over a PV diagram, process 1 to 2 is reversible adiabatic compression, followed by process 2 to 3 reversible constant pressure heat addition, then reversible adiabatic expansion, right, and there is no connecting point between 1 and 4 because this is open cycle. And over temperature versus entropy also you can draw the same process. Process 1 to 2 is isentropic vertical line, followed by the constant pressure heat addition, then followed by the expansion, right, at reversible adiabatic expansion. This is the open cycle gas turbine PVTS diagram. Next one is closed cycle gas turbine. In closed cycle gas turbine, instead of combustion chamber, right, now we are using the heat exchanger. So what is the purpose of heat exchanger? They will simply heat the working fluid. That means working fluid will not undergo any kind of phase change. So the same working fluid will be circulating back and back. We need to take the air from outside, right, and reject the air, reject the combustion product out of the cycle. So we are using two heat exchanger. One is for heating and one is for cooling. So this is the compressor coupled with the turbine, and there are two heat exchanger. One is replacing the combustion chamber, another is working like a cooler. So a certain mass of air circulates throughout the circuit. This is a circuit. So air enters here, getting compressed, finally getting heated up by an external source, right? And finally hot air enters into the turbine. Turbine rotates, you get the mechanical work, right? And finally it is getting expanded, getting cooled in the cooler, and then again cycle repeats. So this can be easily be drawn on a TS and PV diagram. Look at the PV diagram. Process 1 to 2 is isentropic compression, followed by the constant pressure heat addition, isentropic expansion, then constant pressure heat rejection. So this is known as Brayton cycle, right? Same thing you can draw over TS versus entropy diagram. Process 1 to 2 is a compression process isentropically. Process 2 to 3 heat addition at constant pressure, followed by the isentropic expansion turbine and heat rejection at constant pressure. So these are the four basic processes involved in the Brayton cycle. Effect of irreversibilities, right? Usually we are assuming like compression process and expansion process are fully adiabatic, but in reality they do not, right? They do not. Lot of frictional losses will occur. Because of that, irreversibility will be associated in the process. So if we look at the usual process is 1 to 2s going to the 3 and then finally 4s. This is basically ideal cycle. 1, 2s, 3 and 4s is ideal cycle. Due to irreversibility, temperature may not going here, it may slightly higher, right, going to 2. Similarly, expansion may not be going up to lowest temperature, it may be somewhere in intermediate. Because of that, work of expansion will be lesser, right, compared to the ideal case. So net work output will get decreased. So efficiency of compressor is nothing but ideal performance. Ideally, should go up to 2s, right, and 1. So H2s minus H1 divided by, actually it is going only up to 2. So H2 minus H1. This is known as the efficiency of compressor. So ideal compression divided by the actual compression. And in turbine, right, actually it is going up to here. Ideally, it should have to go here. So efficiency of turbine is nothing but actual expansion divided by the ideal expansion. This is known as the efficiency of turbine. So ideally turbine has to produce more work, but actually it is creating less. So less divided by more will give the efficiency, right? Similarly compression, if it is ideal process, it will requiring minimum work, right? Minimum work. When irreversibility is associating, it will be requiring more work. So this quantity is more. H2 minus H1 is more compared to the H2s minus H1. Alright, so ideal compression divided by actual compression ratio is known as efficiency of compression. Actual expansion divided by the ideal expansion is known as efficiency of turbine. Next one is jet propulsion cycle. So if we look at the jet propulsion cycle, Brayton cycles are extensively used for either power producing in electrical power plant, like you can directly couple the turbine right to the generator. You can generate the mechanical means electrical work in electrical power generation plant. Basically, we are using gas turbines right for producing larger quantity of electricity. But extensively, if you find the application, they will be in the aircraft. They are well suitable for the aircraft. So you look at the combination. This is the compressor, right? So it is having a number of stages, maybe 4 or 5 stages. Compressor can be used, right? So this is a compressor coupled with the turbine, and this is the combustor can where combustion will take place. This is the outer casing of the engine. Only thing is that in the engine we are using at the end one nozzle, right? Why nozzle is needed? Nozzle will expand the gas at very high velocity, right? And as a result of that, you will get the thrust, forward motion, right? So it works on the Newton's third law of motion, right? For every action, there is a equal and opposite reaction. So higher the jet velocity, higher will be the forward velocity of the aircraft. So it requires diffuser, right? Here enters into the diffuser, then enters into the compressor, right? Where pressure rises, and finally enters into the combustion chamber, or you can say burner section, where fuel burning takes place. Then hot gases comes on the turbine blades, turbine rotates, you get the mechanical work, and that mechanical work is sufficient enough to derive the compressor, right? No additional work will be produced by the turbine. Turbine will produce just sufficient work which is required to run the compressor, and finally the rest of the gases expands through the nozzle at very high velocity and you get the thrust. So total components we look at, one is diffuser followed by the compressor, burner, turbine and nozzle. So we can draw it here schematically. This is the diffuser section. Purpose of diffuser section is to reduce the kinetic energy to the required limit at which maximum mass flow rate can enter into the engine. So it will here purpose of intake or diffuser is to provide sufficient mass flow rate of air to the engine, right, at appropriate velocity. It comes here, slight pressure rise will take place in diffuser, then further pressure rise takes place in the compressor. So in compressor, this is the compressor. Look at geometry, it is getting decreased, the volume is decreasing. That means your airflow is getting compressed, so pressure will rise. So high pressurized air enters into the burner, then finally partial expansion, right? After the partial expansion, basically it will expand into the nozzle. So turbine will produce the sufficient mechanical work which is required to run the compressor. Clear? So this is the basic funda of the gas turbine cycle that we are using the aircraft engine. So if you draw this over TS diagram, the TS diagram, so process 1 to A is basically diffuser section, and A to 2 is compression, followed by the heat addition. Process 2 to 3 is the heat addition because T3 is higher than T2, heat addition. Then partial expansion in turbine. Process 3 to 4 is the partial expansion in turbine, and process 4 to 5 represent the expansion in the nozzle. This is the nozzle, right? Here turbine, here combustor, and A to 2 is compression, and 1 to A is diffusion. So we same thing we can draw over pressure and volume diagram. Pressures, diffusion process is reversible adiabatic process between 1 to A, followed by the reversible adiabatic compression between A to 2, followed by the reversible constant pressure heat addition in process 2 to 3, partial expansion in turbine isentropically in process 3 to 4, followed by the final expansion in the nozzle process 4 to 5. Then cycle repeats. So we can say the thrust power generated is nothing but thrust generated into the aircraft forward velocity. And how thrust is generating? Thrust is generating due to the momentum change, right? Mass into velocity change, velocity at jet and velocity at for inlet. So mass into velocity of jet, velocity by which flow is coming out from the nozzle, minus forward speed of the inlet velocity by which air is entering in the engine, into aircraft velocity, aircraft forward velocity. The product of this is known as the thrust power generated. Propulsive efficiency is nothing but thrust power generated divided by your propulsive power divided by the energy input. What energy you are given? Heat supplied. You divide this will give the propulsive efficiency of the engine. So it is a measure of how efficiently the energy released during the combustion is converted to the propulsive power. What are the advantages of gas turbine? Gas turbine engines have a great power to weight ratio compared to the reciprocating engine. Second advantage, you can say reciprocating engines are having too many reciprocating parts which will lead to larger vibration issues, right? And in operation will not be smooth, but in gas turbine operation is smooth. So gas turbines are smaller than their reciprocating counterpart of the same power. The ideal jet propulsion cycle differs from simple ideal Brayton cycle. In that case, gas are partially expanded in turbine, right? In jet propulsion cycle, gases are partially expanded, right? Partially in turbine and finally in the nozzle. The gases that exit the turbine at a relatively high pressure are subsequently accelerated in a nozzle to provide the thrust needed to propel the aircraft in the case of jet propulsion. But in ordinary gas turbine cycle, immediately after the expansion to the turbine, it is getting expelled to the atmosphere. In jet propulsion, after expansion in partial expansion in turbine, the rest of the gases are getting expanded in the nozzle. So this is one of the pictorial presentation of the jet aircraft, which is using the jet propulsion cycle. So these are the basically air standard cycle which we have covered. Alright, so if you are having any doubt in this section, right, which we have covered today, feel free to write in the comment section, or you can approach to me by via WhatsApp number. Alright, so next class when we will meet, we will cover the Rankine cycle, that is called external combustion cycles, as well as we will see the vapor compression refrigeration cycle, or you can say refrigeration cycles. So for today, this much is enough. See you all in next class. Have a nice day. Good day.